So for chemical equation, we already learned the components of chemical equation. We learned how to balance them. And now in this lecture, our focus is on writing chemical equations. We want to learn how we can predict the products of a chemical reaction. So once you learn how to predict the products, then you can complete a reaction, you balance it. Now, just a quick review of what we learned about chemical reactions. These are the symbols that we see in a chemical equation. The arrow or yield that always points towards a product. The physical state, solid, liquid, gas, or aqueous are going to be written in parentheses, and that triangle represents the heat in a chemical equation. Also remember the law of conservation of a mass. During a chemical reaction, no mass is produced nor destroyed. So in order to follow the law of conservation of mass, we learned to balance the chemical equation. Balancing meaning that we wanted to make sure that the number of atoms and reactant and product side are the same. Now, what those balancing coefficient mean? So those balancing coefficients basically give you the ratio in which reactant and products need to be mixed. So, for example, in here you see the reaction of propane C3H8 with oxygen that gives you carbon dioxide and water. So I'm just looking at the coefficients. So those coefficients could represent the number of molecules, for example. So I can read it this way, that one molecule of propane reacts with exactly 5 molecules of oxygen, and from that reaction exactly 3 molecules of carbon dioxide and 4 molecules of H2O would be produced. So based on those coefficients, I can also look at the number of atoms and see how many carbon and hydrogen and oxygen atoms need to react in order for carbon dioxide and water to form. So the number of atoms are the same too. What is also very important that we're going to work on it in the next chapter is looking at these balancing coefficients as molar ratios in between the reactant and products. So looking at the balancing coefficient again, I can tell that 1 mole of propane reacts with 5 moles of oxygen, and from that reaction 3 moles of carbon dioxide and 4 moles of water molecule would be produced. So this is going to be very, very important. We're not going to work on these molar ratios too much in this chapter, but I want you to remember this, that this balancing coefficient represents the molar ratio. So whenever you write a chemical equation and you balance it, always think about those balancing coefficients as molar ratio in between reactant and product. These molar ratios later on are going to help us predict the quantity of each product that's going to be produced, or the quantity of reactants needed in order to produce certain amount of products. So let's look at a couple of examples. Again, the goal here is to complete chemical reactions, balance them, but always in the back of your head, remember that these balancing coefficients represent molar ratios. These are going to be extremely important for us because in the upcoming chapters, we want to show you how to do quantitative measurements in chemistry, like knowing how much of each reactant to mix and know exactly how much product is going to be produced. So these balancing coefficients are going to be extremely important because they represent the molar ratios. So for example, if you look at the reaction of hydrogen and fluorine that produces hydrogen fluoride, every 1 mole of hydrogen reacts with 1 mole of fluorine, and from that reaction 2 moles of hydrogen fluoride is produced. Now this is the balanced reaction, but let's say that you do this reaction in a lab, but you want to do 2 moles of hydrogen. 1 mole is not enough for you. So you want to know that if you have 2 moles of hydrogen, how many moles of fluorine, for example, you would need to react with it. So I would say 2 moles of hydrogen, and based on the balancing coefficients, I know that each mole H2 needs 1 mole of F2. So moles of H2 cancel out. This tells me that for 2 moles of hydrogen gas, I would need 2 moles of fluorine gas as well. So we know exactly the amount of reactants that we need. Now, if you use 2 moles of hydrogen gas, how many moles of hydrogen fluoride gas would be produced? So based on the balancing coefficients, we can write a conversion ratio. So we're using these balancing coefficients as our molar ratios. So I know that for each mole H2, based on the balanced reaction, 2 moles of hydrogen fluorides are produced. So moles and moles cancel out. You end up with 4 moles of hydrogen fluoride. We will work more on this once we start the quantitative and mole-to-mole ratio in the next chapter or so. So let's look at one more example and then we move on to completing chemical equations. So you're looking at a reaction of propane and oxygen that gives you carbon dioxide and water. So from this balanced chemical equation, you want to know how many molecules of oxygen are needed to burn 2 molecules of propane. So if you have 2 molecules of propane, you want to know how many oxygen molecules you're going to need. So start with 2 molecules of propane. Based on the balanced reaction, I can tell that each molecule of propane needs 5 oxygen molecules. So therefore, we're going to need 10 molecules of O2 to completely use up or consume the propane. So now let's look at chemical reactions. So chemical reactions are chemical changes that occur. So you start with substances or like elements and you react them. You set up the condition in a way that they react, and from that reaction new materials are formed. So you don't expect the exact same substances that were used in reactants to appear in the products because your reactants undergo a chemical change. You just expect to see the same elements, atoms that were used in your reactants to appear in the products too. Now, the type of substances are going to be different, but the type of atoms that are used in reactants are going to be the same of the atoms or elements that appear on the products. Now, there are some driving forces for the chemical reaction to take place. These are given here, and these are also indications of chemical reaction. So if you mix 2 solutions, if you observe a formation of a solid, if you observe a color change, if you observe a formation of a gas, if you notice that the reaction mixture is either getting hot or cold, those are all indications or evidences of chemical reactions. Now, these could be evidences that we can see, but if you don't see any change, it doesn't mean that no chemical reaction occurred. In order to see if any chemical reaction occurred or not, we have to write the reaction on a paper and see what we expect to get from a chemical reactions. And oftentimes, after you do your chemical reaction, you have to do characterization techniques to to prove or confirm the products that you were expected to get theoretically. So what we're going to learn here in this lecture is learning how to write a complete chemical reaction, meaning that if reactants are given to you, you're going to learn how to predict the products. Now, the type of chemical reactions that we're going to cover are going to be combination reactions, decomposition, single displacement, double displacement, and oxidation reduction reactions. So we're going to go through each type of chemical reactions one by one, and I show you how you can identify the type of a reaction and how you can write the products of a chemical reaction. For redox reaction, we don't need too much of it in this lecture. I'll show you later on what redox reactions are. But for now and for this lecture, we're going to cover combination reaction, decomposition, single displacement, and double displacement reactions. So let's start with combination reaction. So combination reactions are those type of reactions that you have two or more reactants, but you end up with only one product. And that one product contains all the elements of the reactants. So hypothetically, if you have A and B react with each other, you get only one product, and that product contains A and B both. So this is called a combination reaction. Now let's look at a couple of examples and see how we can complete combination reactions. So one type of combination reactions are a reaction of metals and nonmetals. And we already know that when metals react with nonmetals, they produce a salt. So you're looking at a reaction of sodium and chlorine. So sodium and chlorine, we want to write the product of a combination reaction between sodium and chlorine. So how do I write that product? So since it's a combination reaction, we should only end up with one compound. And that compound should contain sodium and chlorine both. So to write that formula, sodium is the metal comes first, and then chlorine. Now when you write the formula, remember that this is an ionic compound. We're still gonna make sure that the chemical formula is correct, meaning the charges need to be balanced. So sodium is in group 1A plus 1, chlorine group 7A negative 1. So this is a correct formula of sodium chloride. Now sodium chloride is an ionic compound. Remember, ionic compounds or salts are always solid as long as there is no water. Now, next step after you complete the reaction, any reaction, is balancing. So one sodium, one sodium. You have two chlorines here, one on the other side. So I put a coefficient of 2, and that means you have to have 2 sodium on this side too. Now this is a complete reaction. So for a complete reactions, you need reactants, products, physical states, and it has to be balanced. That's what a complete reaction means. Now, another type of combination reactions are the reaction of metal oxides with water. From the reaction of metal oxides and water, metal hydroxides are formed. So memorize this, because you need to know this. So from a reaction of metal oxides and water, metal hydroxides form. Now, this is how the question is going to be given to you. We tell you to write the product of a combination reaction of calcium oxide, and water. So calcium oxide is a metal oxide. With water, I know that products has to be a metal hydroxide. What is our metal here? Calcium and hydroxide. Now this formula, chemical formula, doesn't seem right because the charge of hydroxide is -1 and calcium is a +2. So the correct formula of calcium hydroxide is this: calcium cations, hydroxide anions, and this is going to be a solid because this is an ionic compound too. Now after you write the product and physical states, you gotta balance the reaction. So 1 calcium, 1 calcium, 2 hydrogen, 2 hydrogen, 2 oxygen, 2 oxygen. This is already balanced. Now let's look at decomposition reaction. How do we identify decomposition reaction? That's when you start with one substance and it leads to the formation of 2 or more products. Usually for decomposition reaction, heat is required. So here is an example of decomposition reaction. So you start with lead-4 oxide, and upon heating, it decomposes to lead-2 oxide and oxygen gas. Now, predicting the products of decomposition reactions is not always easy, but there are a couple of decomposition reactions that we can tell what the products are going to be. For example, if you have a carbonate, metal carbonate, or any carbonate, could be even carbonic acid too, when it decomposes, it produces carbon dioxide. So notice that from the decomposition of carbonates, carbon dioxide is formed. The products of decomposition reactions, sometimes they're not very straightforward to predict and know what they decompose to. What you need to know from decomposition reaction is identifying them. So if we give you an equation and we ask you what type of reaction it is, you're expected to identify a decomposition reaction. And also know that carbonates, when they decompose, they produce carbon dioxide. So let's look at the other type, the third type of chemical reactions, which are single displacement reactions. So single displacement reaction, they have this general format here. So you have one element that reacts with a compound, and from that reaction, a replacement takes place, and you get a compound and an element. So your element could be a metal, and it's going to replace another metal, which is B. And in order for this to happen, A needs to be more active than B. The other type is that you can have a single displacement of nonmetals too, where A and B are nonmetals, but still A needs to be more reactive than B. So I'll show you examples of all different types. So let's look at this reaction. You get the reaction of zinc metal and hydrochloric acid. So again, let's just assume that this 2 is not here yet. I'll show you where the 2 comes from. This is just a typo here. But I'll show you how we can find these 2 here. So in order to complete a reaction, first we need to identify the type of reaction. So this has a format of a single displacement reaction. Why? Because I start with an element, which is zinc, reacts with a compound, hydrochloric acid. Now, since this is a single displacement reaction, zinc is going to replace hydrogen. Since zinc is replacing hydrogen, meaning that it's going to sit with chlorine, and then we get hydrogen here as another product. We're not done though. Once we do this, we do the replacement, we still have to look at the chemical formulas and make sure that the chemical formulas we're writing are correct. So the correct formula of zinc chloride is zinc Cl2, and hydrogen, remember that it doesn't exist as just H, it's always H2. Now, once you complete the reaction, you gotta balance it. 1 zinc, 2 Cl2. You're going to need to have 2 hydrochloric acid, and then the hydrogens are balanced. Now, remember for activity series, for single displacement reactions, in order for zinc to replace hydrogen, zinc needs to be more reactive than hydrogen. But where do we find that? How do we know if zinc is more active than hydrogen or not? So you're gonna have to look at the activity series. Let's look at this chart here. So we were looking at a reaction of zinc and hydrogen, and we wanted to know if zinc replaces hydrogen. So if you look at the activity series, zinc is more active than hydrogen. So therefore, zinc can replace hydrogen and produce zinc chloride and hydrogen gas. So for single displacement reactions, and only single displacement reactions, you have to check the activity series to see if any replacement can take place or not. And this is only for single displacement reactions. Now let's see how we can write the physical states of each one of these products here. So for the reactants, you know that you have zinc metal and hydrochloric acid aqueous, meaning that aqueous solution of hydrochloric acid. So it's hydrochloric acid that's dissolved in water. Now, in terms of products, hydrogen is obvious. It's a gas. Now, what is unknown here is the physical state of zinc chloride. So zinc chloride is an ionic compound. We've said many times that ionic compounds are solid unless there is water in your reaction. And we have water because hydrochloric acid is an aqueous solution. So now, two things can happen here. Either zinc chloride is soluble in water. In that case, it's going to form a solution. And if zinc chloride is not soluble in water, it's going to appear as solid. So how do we know if zinc chloride is soluble in water or not? So for this, you're going to have to look at the activity series. Sorry, the solubility table. You're going to have to look at the solubility table. So on the back of your periodic tables, or the periodic table that's already posted, you have a solubility table. So 1, 2, 3, 4, the fifth box from the top, it gives you a very small table for solubility rules. So it's not a complete table, but it's just going to be sufficient for our course. Now, on this table, you see two columns, usually soluble and usually insoluble. So you want to look at the solubility table and see if zinc chloride is soluble or not. Now, you won't be able to find zinc chloride exactly in the solubility table. You can figure out the solubility either based on the cation or the anion. So your cation is zinc. We don't see anything about zinc on the table, but your anion is chloride. So find chlorides, and it comes under the usually soluble. So this is how you read the table. Since it's usually soluble, it means that chlorides, bromides, iodides are usually soluble except for silver chloride, lead-2 chloride, mercury chloride. Now, zinc chloride doesn't appear as one of the exceptions. So this tells us that zinc chloride is soluble in water. And since zinc chloride is soluble in water, you write aqueous for the physical state of zinc chloride. Now, this is a complete reaction. So let's look at more single displacement reactions. So reaction of aluminum and copper 2 chloride. So reaction of aluminum and copper 2 chloride, we ask you to complete this reaction. Now, in order to complete, you first want to identify the type of reaction. This is a single displacement reaction because you have aluminum, which is an element reacting with a compound. So single displacement reaction, meaning that aluminum would want to replace copper. But before I go ahead and write the product, I want to check the reactivity or activity series to see if aluminum is in fact more reactive than copper or not. So you find aluminum and copper in the activity series. Here is aluminum and here is copper. So aluminum is more active than copper. So that means aluminum has the ability to replace copper. So aluminum is going to sit with chlorine, and then you're going to get copper metal. Now, this is not a correct formula for aluminum chloride, so we're going to need to have a 3 here. So we're going to first balance the reaction. So 1 aluminum, 1 aluminum. And in order to balance, we're going to need to have 2 aluminum chlorides here. And then 3 copper chloride. And now the reaction is balanced. Now this reaction is not complete yet because we don't have the physical state of aluminum chloride and copper. So copper is a metal. It's always a solid, even if there is water, because metals don't dissolve in water. And then since there is no water here, aluminum is a solid, copper 2 chloride is solid, aluminum chloride is going to be solid too because it's an ionic compound and there is no water. Now let's look at the second reaction. You have the reaction of silver and copper 2 sulfate, which is a single displacement reaction, meaning that silver, if this reaction happens, silver would need to replace copper. Now, before we go ahead and write the products, we want to check the activity series and see if silver is more reactive than copper or not. So here is copper and silver. So as you see, silver is not more active than copper, meaning that silver does not have the ability to replace copper. What does that mean? It means that no reaction will take place. So when there is no reaction, you either write no reaction or you put a big cross, or you write NR, meaning no reaction. If you leave it blank, it means that you don't know the answer. So you gotta write down that there would be no reactions. So let's look at different types of single displacement reactions. Again, the principle is the same. Your metal is going to replace the cation of the compound. Now, that compound could be different types. It could be acid, it could be water. So if you have a reaction of a metal and an acid, you would expect hydrogen and salt. And let's see how that happens. You don't necessarily need to memorize this, but you should know how to write the products. So aluminum element reacts with sulfuric acid, which is a compound. I expect a single displacement reaction. Now, in order to see if aluminum can replace hydrogen, you check the activity series to see if aluminum can replace hydrogen or not. Now, on the back of your periodic tables, right under the box for solubility, we have a box for activity series. So this periodic table will be provided to you in the test. So this is where the activity series is for the test. So use it so you know where everything is. So if you find aluminum and hydrogen in the activity series, you can see that aluminum is more reactive than hydrogen. So aluminum can in fact replace hydrogen. So I would expect aluminum sulfate to form and hydrogen gas. And why hydrogen gas? Because we don't have just hydrogen. Hydrogen doesn't exist as monoatomic. It has to be a diatomic molecule. Now we gotta make sure that the reaction is balanced. So you're gonna need to have 2 aluminum here and 3 sulfuric acid and 3 H2. Now in terms of physical state of aluminum sulfate, you refer to the solubility table. So you should be able to find this based on the sulfate. So all the sulfates are soluble except for some metal sulfates, and aluminum is not one of them. So this is going to be in aqueous solution. So the other type of single displacement reaction is a reaction of metal and water. And from that reaction, you would expect to get hydrogen gas and either metal hydroxide or a metal oxide. So here is an example of sodium and water. And from this reaction, you would expect to get hydrogen gas, and sodium would form sodium hydroxide. So if you look at the hydroxide, solubility of hydroxide, this sodium hydroxide is going to be soluble. And to balance the reactions, in order to balance, we're going to need 2 and 2 and 2 of sodium hydroxide. So another type of single displacement reactions, that's when a metal reacts with a that's when a non-metal or a halogen reacts with salt. So this is a typo here. This should be a non-metal. So when a metal or a halogen reacts with a salt, you would expect to get salt plus that either metal or a halogen. We already did few examples of metal and salt. This is an example of a halogen and salt. So chlorine is going to replace potassium. So chlorine is going to replace iodine. So you get potassium chloride and I2. So iodine is solid at room temperature, and potassium chloride is soluble in water based on the solubility table. So this appears as aqueous, and now we gotta balance the reaction, and this is balanced now. Now the general rule for the reactivity of halogens is that for halogens, as you go down, the activity decreases. So F2, Cl2, Br2, I2, and this is the activity. So this is the activity series for halogens. And as you go down, it decreases. So here chlorine is more active than iodine. That's why the reaction takes place, and chlorine can in fact replace iodine. So let's do a few more examples. So you want to know if a reaction between nickel and hydrochloric acid occurs, and if it does, what are the products? So here is what we're trying to find. We want to look at the reaction of nickel metal and hydrochloric acid and see if this reaction takes place or not. So this is a single displacement reaction. For nickel to be able to replace hydrogen, nickel has to be more active than hydrogen. So we're gonna have to look at the activity series and see if nickel is more active than hydrogen. So if you look at the activity series, nickel is in fact more active than hydrogen. So this reaction can take place, and you get nickel chloride plus hydrogen. And nickel chloride, based on the solubility table, is soluble in water. Now we just gotta make sure that this is balanced, so you're gonna need 2 hydrogen here, 2 hydrochloric acid. So let's look at another example. Will a reaction occur between tin and aluminum chloride? If so, write the balanced chemical equation. So we want to look at the reaction of tin, which is a metal, and aluminum chloride. So this is a single displacement reaction. For this reaction to occur, tin has to be more active than aluminum. Now look at the activity series, find tin and aluminum, and see if tin is more active than aluminum. So based on the activity series, tin is less reactive than aluminum, so this reaction does not take place. No reaction.